my name is Lucille Sachs, and today in this video I'm going to be talking about two calculation of significance problems from the first four topics. And so the first problem is tubing down Clear Creek, and it's an example of Bernoulli's law. And in this problem, the goal is to solve for the freshman who's tubing down the Clear Creek, his velocity here and here. When solving for those velocities, they are only an approximation because we are assuming the flow of the creek is completely steady, and we are also assuming that there are no friction or viscous forces. And none of those things are true, but when we make those assumptions, we can solve the problem. So we start with the simplified Bernoulli's equation, which is right here. And that is a rearranged to solve for V2. I have it in two different ways right there. But we don't know our delta P, but we do know that pressure is force per area. So then we can make this substitution that P1 minus P2 is actually force over A1 minus A2 because the force is constant. So then we can solve for the constant force. And we know that our delta Z is always 1 because it tells us that in the problem statement. And so then it's solved, and V2 is found to be 9.93 meters per second. And to solve for V3, it's pretty much the exact same, except the ratio of areas is different because A1 is now 2 times 7, and A2 is now 25 times 1.5. And then also in this, V1 is 9.93, it's not 2. But then so when those substitutions are made into this, we find that V3 is 8.20 meters per second, so we know that the freshman is going fastest in the middle of the creek. The problem I will be talking about has to do with Sam the Clown and his crazy balloons. The first part of the balloon problem asks how much force a 20 kilogram child would have to apply to stay stationary if it was being blasted by a 100 balloon. And this is an example of a macroscopic momentum balance. So if we start from that, we are at steady state, so this goes away, and based on where I drew my boundaries, there's nothing coming in, but there are the balloons going out, and that is plus the sum of the forces. So then that will simplify down. We can then do a substitution for m dot because we don't know what it is, and put in rho av, so then we'll have rho av squared is actually our force of balloon instead of m dot v. And then but that is just the force of one balloon, so then you multiply it by 100 for the 100 balloons, and then 3.113 newtons is the force that the child has to exert in order to stay in place when being blasted by 100 balloons. The second part of the problem asks to solve for the maximum weight of an object that could be attached to Sam's balloons that he accidentally lets float off, which is an example of Archimedes' law. So a force balance shows that mass times acceleration will equal the sum of the forces. And then we know that mass is maxed when acceleration is 0. So then we know that the sum of forces is equal to 0. This is Archimedes' law, and then we know that the weight is just mg. And then we know that the mass total is going to be the mass of the object and the balloon. And then rearranging all of that lets you solve for the mass of the object, which is 10.6 grams. The last part of the problem asks to relate the pressure of the atmosphere where Sam the Clown usually blows up his balloons versus the bottom of a 7-meter pool to show the difference in pressures there. This is an example of hydrostatics. So we know the atmospheric pressure because it was given. And then we use the hydrostatics equation, which is PATM plus rho GH. We get this answer for P2, and then we can relate P2 to PATM, which gives us 1.75, and so that would be the pressure difference of him blowing balloons above water versus below.